Good afternoon, everyone. I'm Jeremy Picot-Clemente, Technology Manager at EPIC. I'm really pleased to welcome you for this EPIC Online Technology meeting on photonics for Earth observation and monitoring. A few words about EPIC. So EPIC is the largest industry consortium in the field of photonics in the world, with more now than 800 members, covering all the photonics applications from space and defense to medtech and quantum, IVR, for instance, as well. Our members are also covering all the value chain from component manufacturers, design and simulation companies to system integrators and end users. And we aim to make the European photonics stronger and sustainable. And how we do this? So EPIC proposes several services to members. So technology support, market and technology reports accessible only for members, networking events, access to new markets as well, mentorship, HR support with the Jobs in Photonics website, and also investment support and connection. Here is the EPIC team. So we are all passionate by photonics, working from home all over Europe. I am a part of the technology team in charge of optics and space and defense, with my colleague Antonio Castello in charge of biomedical and laser technologies, and Ivan Mikitsky in charge of integrated photonics and quantum market. And among EPIC, we also have a team dedicated to marketing and a team dedicated to event management. I would like also to show you today the next EPIC event we will organize, so physical meeting and online meeting. So about physical meeting will be next week at W3 Fair in Wetzlar, Germany, where we'll organize two different events, the Tech Watch and the VIP Breakfast. Then we'll have events also organized at OFC in San Diego, USA, a members run and a members lunch. We'll have also this VIP networking reception. And then in April 16th to 18th April, we'll have the annual general meeting 2024 organized at Juan-les-Pins in France. And a meeting which also could be really interesting for you is the one we'll organize in Oslo, Norway at DG Food. And it will be focused on agriculture and food industry. And about online meetings, online events, we'll have in 2 weeks photonics for quantum computers, so EPIC OTM on quantum computing. Then an EPIC market report on spectral imaging presented by Thematis, which also could be really interesting for you. The 20th of March 2024, we'll organize something online on marketing, on social media, special focus on B2B companies. And in beginning of April, we'll have an OTM on photonics technologies to improve pharma processes. And then we have also this EPIC online session on membership benefits, information, and updates. EPIC is also part of several European projects, as you can see on this slide. So Photon Hub, an innovative hub offering comprehensive range of supports to industry. JPICS, the manufacturing pilot line for indium phosphate PICs. MedFab, a pilot line dedicated to new photonics technologies for medical diagnostics. Fabulous, the European pilot line for the manufacturing of freeform micro-optics. And Pulsate, an European network for empowering SME digital competencies in laser and additive manufacturing. A quick overview also of the participants of the today's meeting. So as I said at the beginning, we try to cover all the photonics industry and all the value chain. And as you can see, we have today participants from all the value chain, from components and module manufacturer to end users and integrators, including equipment manufacturers, materials companies, metrology and testing companies, service providers, research and development, of course, contract manufacturer, software and design companies, distributors, and also consultancy companies. Few words also about photonics for new space in terms of application. So we can find agriculture application, environmental monitoring, disaster management, climate change, also climate change monitoring mainly. In terms of technologies, we can find remote sensing, remote sensors technologies, LiDAR system, hyperspectral imaging, and also high resolution imaging as well, optical communication for data transfer, and also spectroscopy-based technologies. In terms of benefits, where photonics is involved. So it can provide high precision, remote sensing, real-time data, and cost effectiveness. We have still a lot of challenges in this industry. So miniaturization and size constraint is still one of the main challenges we can find. Reliability in harsh environment, of course, cost reduction, data processing and analysis, and also, of course, standardization. And as we can see also about market forecast, this market is now really dynamic and full of business opportunities, not only for big companies, but now also for smaller companies, startups, and SMEs. And this is also why this industry is attractive compared to 2000s, where this market was maybe less open to industry. So it's really nice and interesting also to have a look on the evolution of this market and industry, which is really promising for photonics industry. And EPIC aims to play a role and support you to take part of the new space journey. And here is the agenda for the today's OTM. So we'll start with Keval Datani, CEO and founder of Spacepower. Then Andres Cifuentes, CEO and founder of IC Optics. We'll continue with Bavo Delore, principal member of technical staff at IMEC. Stephen Hancock, director of the NERC field spectroscopy activity at Alter Technologies. We have also a presentation from Jean-Luc Gache, founder and CSO of First Light Imaging, Matthias Beer, CEO and co-founder at Space Optics, and last but not least, speaker of the day, so Trond Loki, CEO of Neo North Electro Optic. So thank you very much for being here. You will have time, of course, to ask the question after each presentation. We'll have 3-5 minutes for question and answer. So feel free to raise your hands through Zoom or write your question in the chat today. And thank you again for all of our speakers for taking part of this OTM. And now let's start with our first speaker, Keval Datani, CEO of Spacepower. So Keval, you can start your presentation and share your screen. The floor is yours.
Thank you very much, Jeremy. And so I think it's quite interesting. I'll be starting off kind of talking about not necessarily like photonics that will be used for Earth observation, but actually photonics that can help do more Earth observation missions and use more different kind of technologies and instruments. When we're looking at things like thermal imaging cameras and things, they're very power intensive. And I want to show how I'm looking at pushing up the availability of power in space so that we can use these in the small CubeSats that are pushing Earth observation today. So what Spacepower does, we essentially use photonics all the way from the beginning to the end of our chain, essentially using laser power beaming in order to recharge satellites directly onto their solar panels. So we've got many different applications that we're looking at. So I think more specifically for here, we're looking at LEO constellations and kind of looking into clusters as well, which might be an interesting alternative methodology, which I'll go into a bit later. But also there's anything with a solar panel is what we can beam to. So I'll also walk through a bit of our multi-junction technology, which is a first of a kind, allows us to beam to a solar panel, even if you don't know what it is. And we started to see some really interesting applications as well for lunar missions, especially for things like rescue and emergency missions, where you can see the Japanese SLIM satellite, landed upside down, and then you're basically kind of hoping that the sun will kind of come and recharge it enough to be able to start using it. So we aim to be able to provide these wireless power services and essentially kind of move towards things like asteroid prospecting in the next few decades. So that's really where I get quite interested. So who are we? We manufacture and supply laser-based power banks for spacecraft. That's the best way to think about it. So like your mobile phone, you don't carry around 100 mobile phones with you just because you use them a lot and your battery runs out quickly. You have a recharging system, which is much cheaper and much more efficient. So this is essentially what we're looking at. Why are we looking at constellations of hundreds and thousands of satellites? essentially it's because these CubeSats are running for, less than 5% of its uptime. So when you're really thinking about the value generated for the asset, the amount of time, sweat, and tears that it takes to launch something into space, we're really trying to help that sustainability angle and really make the most of what we've got up there. And so really the big magic bit is our a technology which allows us to beam to any solar panel. So most of the industry uses triple junction solar cells, and that can complicate things like power beaming quite a bit. And we've developed a system which allows us to beam to anything, to any, especially triple junction or less solar panel, and provide power even if you don't know what your solar panel is. And really what our aim is to launch in 2025 with BAE for a first of a kind mission in order to work with their cluster system. And this is where we see quite a lot of the LEO uses, so low Earth orbit. Sometimes a lot of your instruments do take quite a lot of time to recharge. So if you've got a heavy synthetic aperture radar, for example, or even if you pushed yourself into a thermal imager, you'll find yourself in an operational mode where you're charging your satellite a lot more than you're using the value generating assets. So when you can work in a cluster, let's say you've got satellites flying in formation, you can actually then distribute power as you need it, rather than telling your customer, oh, can you wait 5 more hours for a rescan? Actually, we aim to be able to deliver this in 1 to 2 hours. So this is generally what our system looks like. Call it the SPOC module, the Space Power Optical Charge. And essentially, we've got a bunch of lasers, 2 sets of optics, one for beam transmission and another one for seeing, like a telescope, so that we can see our customer, recognize where it is, and then make sure that we're sending the power to the right satellite. And we're looking at things also for geostationary, looking at things power levels going up to 400 watts. And then, as an aside, I've also done some initial designs for lunar environment, where you're really thinking about lunar dust, the radiation levels that you have there. And it's a weird place with lots of orbital anomalies. So gravity is not actually consistent. And this is kind of what we look at. We're looking first at power banks. So the same module basically breaks out into power banks. So we individually sell that to customers. And then looking forward, actually trying to help minimize the amount of batteries that people need to incorporate into their satellite and enable something like a flyby laser. So, you actually just hook up to our constellation of lasers, and we can then give you constant or ad hoc power charging. And this is our little rover. So that's my little technical demonstrator. It's got its own recharged battery powered by a laser. So it allows me to drive my car wherever I want. The laser's tracking the rover with a automated recognition and tracking system, and make sure that we can see how much power is being delivered back at the control center. So this is our kind of like key competitive landscape. The real big thing is the backwards compatible technology, and being able to already serve commercial customers. So even if, the big thing is that a lot of the satellites that are up there in the market that's out there today are satellites that were launched, 15, 20 years ago. But really what we want to do is to move into the LEO small sats, where we see a massive value proposition where you can use more of your satellite for things that generate value rather than keeping yourself alive and having your power. So in overall, this is kind of what we look at. We look at our power performance, range performance. Those are the 2 kind of like defining characteristics of our system. And it's really based around lasers and optics, with the receiver being a photovoltaic. So kind of working closely with suppliers to look at how we can really push this performance as big as possible, looking at, wide spectrum optics, but also kind of like high power lasers with great beam quality. And I can just go into, some of the little technical challenges where we're looking at diode lasers, which have a very elliptical kind of beam, and basically trying to think about how do we shape it so that I'm delivering most or all of that beam to my customer at the end of it. So this is one of the projects that we've got signed up. So this is the launch going into 2025, and kind of really puts it into perspective what the issues are. Sometimes one of their customers will complain to us and say, look, we asked for a scan over this area, and we missed the scan. The ships had moved, and we asked for a rescan. We don't know whether the ship is sinking. There's a smuggling operation. It's been hijacked, and the customer or the data provider has to tell them, sorry, you've got to wait 5 hours, and it's just too long. So if you've got that charge waiting for you that you can distribute quickly, you enable a lot more performance for your satellites. And we're really working kind of with US Naval Research Labs, who've already demonstrated in-orbit laser power beaming earlier last year, and just kind of gives you an outlook on where we want to push this. So rather than looking at about 1.5 watts being delivered, we're looking at 15 watts being delivered, and going over a kilometer, push the efficiency and make it compatible for everybody. And this is kind of like the overall, where are we and where are we going? This year, we aim to have our minimum viable product build, which allows us to basically, we've scoped out all of the base components, get the space qualification, and really just understand for ourselves, the thermals are going to be the biggest challenge in this product. So how do we ensure that we can keep our lasers on safely for the longest amount of time without degrading its performance and lifetime? That's the quick kind of whistle-stop tour, but then I'm really open to questions and happy to delve into more information.
Thank you very much, Keval. Thank you very much for the nice presentation. It's good to see that you progress a lot since a few years now, so that's really nice to see also your roadmap. So any question for Keval, you can raise your hand through Zoom. So it's quite clear what you can offer, Keval. I would like just to ask you maybe what could this community, I mean the Photonics community could provide to you? How could you work with them? Do you already work with some of these companies, and how you do this usually?
Yeah, absolutely. Really a lot of where we are is just developing and proving out that last bit of core tech, which is the optics. So it's been something where we've done a lot of our development on the laser to the photovoltaic. Now the challenge really is kind of increasing that distance as much as possible. I'm talking with Andres as well from ASC Optics to kind of work through a lot of the space focused challenges that we have. But really just from the community, it's trying to understand I think it's the subcomponents that are most important for us. So things like laser drivers, high power laser drivers, high power optical fibers, particularly wide spectrum to enable us to kind of achieve, all the way from 400 nanometers up to, 1400 nanometers, and kind of make that transition. For the thermals, I've got that covered. It's really kind of looking into the optics. I want to get that beam delivered from that laser source, transmitted out in the best way possible. I mean, I think the best way to summarize us is a photon transportation company. So yeah, anyone that can help us with those kinds of things would be fantastic.
Good. Thanks, Kevin. Yes, we have a question from Martin Walls from Tronic. Please, Martin.
Yes, hello. Thanks, Keval, for your presentation. That's great. A very interesting idea. I take it you're thinking about where to get the photons from. My question is, how do you know where to send them? Yeah, how do you find the target?
I mean, what's great is with the system with BAE, they've got the intra-satellite links all organized. So we're talking with the system that we're designed for. In that sense, that's the busy kind of area when we're talking about low Earth orbit. So either having some kind of end-to-end communication link, that's really what we would like to have. When we're looking at our immediate market, which is in geostationary, we're looking at these retired satellites. They kind of sit by themselves in an empty ocean. So it's quite easy for us to get up there, have a look, make sure that we're in target. And this is where that long range telescope system works, so what we're looking at is a CMOS sensor at the back, with pretty standard optics. I mean, Andres, you're definitely more expert than me on this stuff. So, this is what we're talking about. So how do we kind of have those sets of optics all working together? And then for the transmission side, it's, just linking the pointing system, both off the satellite, but also off the internal optics to make sure that we're delivering to the customer.
Thank you, Keval, for answering the question. Yes, we have a question from Scott Berry for Power Photonic. Scott, please.
Thanks, Jeremy. Thanks, Kevin, for the presentation. It was really interesting. So I just wanted to introduce ourselves. So we're actually an optics manufacturer of low SWAT optics, mainly in defensive markets, but we also have a range for material processing and high power applications. So it'd be good to grab your details and I can maybe send you over some information on what we could potentially offer.
Absolutely. Yeah, please do. If you've got my contact details, otherwise, we can
I can drop you a message in the chat. We'll go from there. No, thanks. Thanks, Jeremy.
Cheers, Scott.
Cheers.
Thank you, Scott. Perfect. That's good. And we have a question in the chat from Yves Pommier. If do you want to ask your question by yourself? You can do it from Institut Schiller. Okay, I can ask it. So the question: what about blinding the satellite during the flyby, Kevin?
Yeah, it's a great question. The main thing is that we've got really low power levels when we're starting off. So really, the safety case is if we're not more powerful than the sun, not more intense than the sun, your optics are going to be absolutely fine. So we don't really see any issues until we start to push that power level. We'll have much more issues in terms of power generation before we start to get to issues like having too intense a beam for some of your sensors. I mean, the point is as well, if you know what you want beforehand, actually we can put filtering, we could put filtered coatings onto the aperture for any of those sensitive sensors, and just absolutely filter out specifically the laser wavelengths that we've got on board. So then it'll be invisible to any of your sensitive instruments.
Thank you, Kevin. Thank you, Yves, for your question. Any other question? Maybe your last one. Okay, and thank you again, Keval. Thanks a lot for participation. And if you want to be introduced to Keval or any of the speakers, you can come to us, and we'll be pleased to do it. Thanks again. So let's continue with our next speaker. So Andres Cifuentes, CEO and founder of AEC Optics. So Andres, we'll start this, and you can start presentation. So maybe you are muted because we are not hearing you.
Hi.
Yeah, good.
Unmute? Am I off mute? All right. Okay, thank you very much, Jeremy, for this invitation. It's great to be here again. Great to see everyone and hear everyone in the audience, both new faces and new names, and also great colleagues as well. I was going to talk about a little bit about what we do, about optics or imaging in general, which is where we come from as a company, and myself and my co-founder as well, and how we're applying this into some opportunities in space. So just a little bit of background of how we got into this whole space thing was, we come from a bit of a defense background, my co-founder and myself. Also worked a lot as a company in science and research, which gave us a lot of background and breadth of solutions for very different types of complicated imaging and photonic systems. And then we couple that with working in fusion and nuclear environments, and particularly in diagnostics for fusion to look into the in-vessel, so the vessel where the fusion reactor takes place in future fusion reactors. Gave us a lot of experience in harsh environments, which is one of the things that Jeremy mentioned in the beginning, which is quite true. We need to be able to work in harsh environments. So space kind of, has a lot of those things: radiation, harsh environments, vacuum, that we already had experience with, and that's how we got started in space. So I'll talk about really quick about some solutions that we have in SWIR, some that are, and then the rest, like I said, we're starting out in this. So in looking into long wave infrared, an example of a project that we just recently won just at the beginning of this year. I just mentioned a few applications which will lead me into finally, what can you do for me and what can I do for you? The EPIC question. Okay, so this is when our heritage and our successful project that we did for the Astrophysics Institute in the Canary Islands in December. The second version of our optics was launched with a satellite, giving excellent results. This time it's a bispectral imager. They're all in the SWIR range. And our customers are using this to detect levels of humidity. And these are actual images taken with our optics flying over the south of Spain. And it's absolutely spectacular. What they're doing is a comparison here between, I don't know if you guys can see my mouse. But anyway, the Sentinel on the left.
We can know this.
Drago so Drago 2 is the optical payload. That's what they call it. Our optics is the SWIR objective lens, 150 millimeter focal length. It's giving about 30-meter resolution on Earth, low Earth orbit. For the cost, is what I always tell everyone, for the cost and time that it took us to develop this, the comparison with Sentinel that was, millions of dollars and many years, this took us 9 months. So I think the comparison is really, really interesting. Anyway, what they're really looking into here is, natural disasters, climate change. So in this particular area in the SWIR spectral band, they're looking at levels of humidity. So that's, we'll see as an application, things you can do, information that you need and you can get that other people will find valuable. Humidity, agriculture, I'll show you a little bit more. So example 1, SWIR. Then another project that we're working on and will be finished soon, hopefully launched in the next couple of years, is this one takes time because we have to find more money. But this one is working in the long wave infrared. And I really like this application because it's very commercial. It's for sustainable farming. We're working together with a great group of companies and research centers. And it takes into account the full chain, which I really love, because the first thing is, if you don't have a good image, we used to say, you can't get something where there's nothing there. So we got to start with a good image. So luckily, they'll still have a job for me. But in the end, we keep moving more and more into the value chain of, now we got to get a good sensor, and we got to start doing interesting things in artificial intelligence, training data sets, data fusion with other information. And one of the things that I really love about this is the flexibility and scalability approach that we're taking with this long wave infrared spectral imager, because it does have various bands, and that's going to be very interesting for helping push sustainable farming at a global level. And I'm a hardware guy, so I'll show you obviously some of the hardware stuff, which is really cool. Optics and optomechanics coupled with these, it's a three-band sensor. This is a drawing, but we're actually making it now. And again, it's long wave infrared, uncooled. Pretty high resolution for a long wave, and really great on-ground resolution. I think we're targeting less than 5 meters. So very interesting, very compact for the resolution it has. And we did a great work in really reducing that form factor. And that's another thing that Jeremy mentioned right at the beginning. Size, weight, and power is a big thing. And then finally, am I doing on time? Yeah. Okay. So finally, the last example, where this is kind of combining those last two, because in this project we're working again. It's I'm showing most of the R&D things because we're looking into the future of Earth observation. So here what we're looking at is shortwave infrared and long-wave infrared, and it has to be very, very small because, ideally we want to use this for space. So we want this project to help increase production capability in Spain. The way to do that for us is how do we make space-ready series production? And that's something that we're looking into and investing in. And to give you an idea, if we try to fit something that's under a kilo so that it works, one of our challenges is to put this into a stratospheric globe, like a balloon. Sorry, in Spanish is globo, so balloon. We could use it for space, but that's really hard. The pointing is very difficult. So that's why I put on this. It has to be very lightweight, and it has to be autonomous because there's got to be a whole bunch of balloons flying everywhere, or you could transfer that to satellites. We did some advances already. It's something we've already made. It's 150 millimeter as well. Very tiny objective lens, like literally like 2 centimeters. And it's very, very light. So this could be one of the solutions and could help towards that weight and power, reducing weight and power. And in this particular project, we're also mixing in integrated photonic chips for, we're looking into the back end of the processing. And I think that'll be very interesting to kind of, start mixing those things in terms of trying to save a lot of power. I think that the tendency is going to go towards onboard processing. And that's going to be where Keval's company is going to be very interesting because onboard processing, it's great. Everyone wants to do it, but it's very power consuming. And I'm really looking forward to working with Keval on that and helping advance in that area to really push that onboard processing. That's another part of this project, as well as with Moderator and some other things that we're working on. So for me, I kind of see that the push in terms of more commercial applications that I kind of like are sustainable agriculture, which I mentioned, mining, which was surprising for me, but there's a interest in that, quite a bit of commercial interest in mining, archaeological site locations, which was also kind of interesting, using spectral data, really cool. And then I see there's a chat later on with much more experts than I am, of course, on greenhouse gas detection. So I'll be really interested to hear about that. I think it's great. Long wave and SWIR, that's going to be great in that area. And of course, natural disasters and climate change. And another one that I just like because it's fun is like looking at boats in the ocean and looking for pirates. So that's pretty cool as well. And with that, I'll finish up with the EPIC question. What can we do for you? As I mentioned before, we're a very fast and agile company in making optical systems for Earth observation. And I want to throw in there space situational awareness, which is something that is going to be quite interesting as satellites also need to see what's around them. And as there's more and more stuff in space, that's going to be more and more interesting. And we have already done some work on that as well. Image processing, which we're keen on. And I would summarize as like a full optronic product cycle. We manufacture products for our customers in series. And that's why we're pushing that, scaling up in production as well. What can you do for us? We're really keen on space-qualified high transmission AR coatings. That's really important for us. And I put AR, but it could also be reflective coatings. Really interested to see stripe coatings for the hyperspectral or multispectral imaging on sensor. That would be great. And then back on the sensors, extremely lightweight sensors to match our extremely lightweight optics would also be of interest for us. And with that, Jeremy, thank you for this opportunity, and thanks everyone, and open to any questions. Thank you.
Thank you very much, Andres. Thank you for this nice presentation. So we have already one question from Jorge HEF. Jorge, do you?
Yes, can you hear me?
Yeah. Yes.
Thank you, Andres, for this interesting presentation. I have a couple of questions. First of all, concerning the PERTE initiatives you have shown, I guess the optronic systems there are uncooled, even in the long wavelength range. Am I right or not?
In principle, we want to look at uncooled because in this kind of new space market, size, weight, and power, right? And I would add cost. So cooling takes power. There's not a lot of space. And and it takes size, but there are some strategies to cool down the detectors in a passive way. So I would say let's say we avoid active cooling in terms of a traditional cooled mid-wave infrared or long-wave infrared bolometer. But definitely there's got to be some strategies in heat management for sure.
And two things, just to let you know, in both regions of your interest in the infrared range, we are space qualified, not only in anti-reflective, already flying, but also compatible in at least hybrid integration mode with black coatings.
Okay.
Our black coatings is, in terms of price as well, is very competitive because we have a patented way where we don't use gold to absorb.
Wow. Very interesting.
So our prices are very interesting on this, all qualified. Some of our colleagues here already know a little bit about it. They have experience on this. And just a question, open question, a reflection to share with everyone concerning this LEO emerging market. I'm very interested in this type of sensing applications, is that optics, photonics in general, can play a role, a very significant role in this weight and power optimization, exchanging the typical mechanical encoders for the engines with optical encoders. We already have optical encoders on some nanosats already flying, which photonics may play a key role there, just to let everyone know.
That's a very, very good point, Jorge. Thank you.
Welcome.
Yeah,
Thank you,
exactly.
Jeremy.
Thank you, Jorge. Thank you for your question. Thank you, Andres. Yes, and we have another question from Julien Boucard from Coherent. Julien?
Yeah, thank you. Can you hear me now?
Yes.
Okay. Thank you very much for the very interesting presentation. Maybe it's a naive question. I'm a bit new in this field, but you're mentioning SWIR and long wave infrared. What are the illumination sources for that, or is that a passive illumination? And what is the wavelength range you mean by SWIR and WIR?
So SWIR, we usually refer to about 1 micron to about 3 microns.
Okay.
To be honest, really, to like 1 to 2 to be fair. Long wave infrared, we're targeting about 8 to 14 microns, depending on 8 to 12, 8 to 14 on the Moderator project. We're pushing beyond like 12 to 14 as well. Illumination sources is the sun, so there's no active illumination. It is in fact passive. Or if it's a thermal source like long wave infrared, it's the heat source itself, because you're detecting electromagnetic radiation that's coming off a heat source. So those are for shortwave infrared, it's definitely passive, and unless we can use some big laser to shine something on it, but that's not going to be the case. It's a passive. So combining these, as what I mentioned, that other project, combining these gives you a more chance of 24-hour operation, or the 24-hour doesn't make sense in space, but like around the globe operation instead of just one waveband. But very good question, Julian. Thank you.
Oh, thank you.
Thank you, Julien. Any other question yes, we have a question from Daniel Vasser, shot from, sorry. So Daniel, you can ask your question.
Hear me?
Yes.
Okay, good. So thanks for your presentation, very interesting. Quick one, are you considering the chalcogenide glass for the infrared? Because as you maybe know, the density is quite lower compared to traditional raw material, and that could be a good solution for gaining weight. And by the way, we do produce such a glass, so,
I'm very aware. As a good optical designer with my background, I will never put the prescription data on a slide. But yes, we are considering, and in fact have used and are using chalcogenides. I think it's a great material. Yeah, I'm quite aware of SHOT's capabilities there, and I do agree it's a great material for the long wave infrared. Thank you.
And then on coatings, we can also provide quite a lot of different coatings qualified for space applications. So like a bunch of filters or let's say multispectral filters or such kind of things. And also anti-reflective coatings for solar panels as well. So that's
okay. I was not aware of that. Thank you. That's very interesting. Daniel.
Thank you.
Thank you.
Thank you, Daniel. Thank you. Okay, thank you again, Andres, for the presentation.
Yeah,
Thanks a lot for your participation. And now let's move to our next speaker, Bravo Delore from IMEC, so principal member of technical staff. So Bravo, you can share your screen and start your presentation.
Yes. Thank you very much, Jeremy, for the introduction and the invitation for presenting our work in this event. So my talk is on-chip spectral imaging for Earth observation and the activities that we are doing here at IMEC on this topic. And as you all know, we are facing very exciting times in Earth observation. From one side to the user side, where user expectations are increasing due to the lots of image data and information as accessible, where even always higher spatial resolution and temporal resolution are being requested from the user in order to connect all this data into the digitized world where we are currently acting in. Furthermore, Earth observation data is really showing its added value at an exponential pace. And global observations are becoming much more easy with the introduction of a constellation of tens or hundreds of imagers. So that's on the user side. On the technological side, there are also a lot of advancements ongoing. Miniaturization of the platforms and the small satellites are an important one. Disruptive change in access to space has opened a lot of new opportunities that has pushed technology forward. A lot of activities in instrumentation and instrument miniaturization have also been taking place, and our technology is also focusing on this miniaturization aspect. Another important change is that it's really an industry-driven sector where we are acting in. So as IMEC as an R&D organization in microelectronics, we have developed a new technology where we have doing spectral imaging, where we deposit thin film coatings directly on top of the chip. So we do it in our clean room, where we are able to do it at the wafer level, and where we deposit the thin filters on there. The big advantage of our facility is that we can do very accurate processing, and we can do lithographic patterning of the filters, meaning that you can go very wild in terms of geometric shapes in which we can create and deposit filters with our technologies in our clean room. So those capabilities have allowed us to create optical filters directly on the chip. Here you see some pictures of examples where we did it on CMOS image sensors, and where we can have a very robust implementation of an optical filter, which is also very compact since it's integrated inside the wafer. And we have the capability to really put different optical filters at different pixels. In addition to that, due to the fact that we do it in our semiconductor fab, it's also a very extreme clean process that of course has a lot of advantages for integrated into your optical payload. And here you see a number of examples that we have built into the Veneer spectral range for CMOS detectors, but we also have examples where we deposited the filters on substrates that are integrated in shortwave infrared detectors. So here you see a picture of the important tooling that we're using for this. So it's an optical deposition tool that is installed in our clean room, and that's basically the star in our work that allows us to do these special optical filters that we have created. We have worked in the last years a lot on having this process much better under control, so that we are now able to create filters with less redundancy built in, and so that we can really exploit the strengths of our deposition toolings. I've here's one example in the project that we are currently working on with a Belgian consortium, and here we created an optical filters for a veneer application, where we combined both optical filters in two ranges together with panchromatic zones at the detector to make sure that we can create all kinds of imaging modes in our camera. And that's the big strength of our technology. Due to the fact that we can do it very accurately, we have make a very efficient use of the focal plane, and this way you can do all kinds of nice things with your instrument. In this example, it's an optical payload that goes on an Earth observation mission on a small satellite, a hyperspectral imager, where we have made it possible to do also digital TDI on this hyperspectral imager to increase the performance and the signal to noise ratio specification of the instrument. So in our unique filter deposit technology, because of its high accuracy, allows to have a very easy solution for the integrator. There's no need anymore to do a post alignment between the optical filter and the image sensor array, because we really do it in one process and basically deliver to our customers, which are typically camera builders or payload builders. We build a full spectral detector at hand, which is a very compact solution. At the same time, we are very able to have a very accurate or efficient use of the focal plane. So this means that we can do all kinds of filter patterns. We can do line-based patterns. We can group the pixels. We can easily go down to the Bayer-like patterns, where we can combine different filters. So we have created 4x4 or 5x5 mosaic type of filters, which are having something like 16 or 25 different spectral bands. Due to the fact that you can create mosaic patterns, you can also make deviations from the standard line-based imaging, which is often being used in Earth observation missions. But you could also do snapshot imaging, where you with one image create a full overview of the scene that you have in different spectral band. Also, video rate imaging is supported by this type of filters. And that's linked, of course, to the extreme design flexibility that we have in our design process, in our deposition tooling, where you can do lines, mosaics, or also combinations of those type of filters. This design flexibility also allows to really make filter profiles not just optimized for the imaging part, which is the normal way of doing it, but we can also create filter profiles that are optimized for the computational and post-processing steps that you do after the image acquisitions. And as we see more and more activities and trends ongoing in compact systems where data processing is done on board, this is also an advantage that we can bring with our filter technology to do, for instance, compressed sensing or other computational imagings. So that's what we are offering with our technology as IMEC. In return, we looking for parties that are looking for compact imaging solutions in the veneer and shortwave infrared range that build cameras and payloads, where we can team up to realize your space endeavors that you are following. If you want to know more, you can always look into the QR code behind that brings us to the different solutions that we currently have available for different applications. Thank you very much for your attention.
Thank you, Babo. Thank you very much. I'm really impressed by your capabilities. Any question for Babo? So it seems that we have a question from YouTube. Could you clarify what is the pixel pitch size of these electro-optics imaging sensors? Do you have some things to tell us regarding this?
Yes, we do it for different detectors. So we have demonstrated this for detectors with pixel sizes for 10 and 5 microns and even smaller ones. So due to our accurate deposition techniques, we can really go to small pixels.
Okay. And regarding Babu, regarding this project you mentioned during your presentation, do you have already some interesting result to share with us?
Well, the slide that I've shown is currently a payload which is under development. So where the flight model is currently being developed and tested on ground. In addition to that, we already have some of our sensors being operated in space by some of our customers. Unfortunately, they do not allow us to share too much details of the data. Okay. So with a bad feeling, we have to say that we cannot show the images.
No problem, we understand. Well, any question? Okay, so thank you again. Thank you again, Bavo, for your nice presentation. Thanks a lot. And now let's welcome our next speaker, Stephen Hancock, Director of the NERC Field Spectroscopy Activity at Alter Technology. So Stephen, are you here? And
hi.
Yes, you can. Yeah. Hello, Stephen. You can share your screen and start your presentation.
Yeah, so hopefully you can see that there. Is that working okay?
Okay, we can see your screen, but can you launch? Yeah, perfect, it works. Yeah.
Okay, so I'm Stephen Hancock I'm actually from the University of Edinburgh. I'm working with Alter Technology on this project, but I'm University of Edinburgh, which is where the spectroscopy facility is. So we are working on a future spaceborne LiDAR mission constellation concept with complete coverage, working particularly with places like the Fraunhofer Centre for Applied Photonics, UK Astronomy Technology Centre, Alter, and Red Wave Labs as well. So I'm a remote sensing scientist, so I've started off talking about why we need the data, but I'll get on to the what we need to make the data possible in a minute. So I mainly work on vegetation remote sensing, and still to this day, the land use change and the growth of plants is the biggest uncertainty in the terrestrial carbon cycle. We just don't know quite how much they're sequestering as they grow, and when they're being chopped down and burnt, we're not quite sure how much is being emitted from it. It's a big unknown in monitoring and verification of carbon credits, that type of thing. Forest fires also very important for that, and biodiversity, nature credits, something that people are very interested in trying to monitor. Biodiversity, habitat structural complexity of forest drives that. Commercial forestry are also very interested in knowing when to harvest their timber, and there's more work recently showing how mental well-being is linked to green space, biodiversity, habitat access, that type of thing. So we've been, I worked on the JEDI mission, the NASA JEDI mission, which is a fantastic LiDAR just been turned off a year ago that fires laser pulse down at the ground. And from that, you can measure the structure of the forest. You can work out where the ground is, measure the bare earth topography, measure the height above and the density of the forest. It's the best way for measuring biomass and structural complexity, which is a useful indicator of biodiversity. There's been lots of spaceborne LiDAR missions over the last few years, mainly led by NASA, but with ESA launching a few, and CNSA over in China launching one. Last year was a bad year for LiDARs, with 4 of them turned off, but there's more interest in future LiDARs. They're all providing unique data sets. The problem with them all is they have very, very sparse sampling down to the power requirements. I was really interested in that first talk. If you've got a way of upping the power of these instruments, you can increase the coverage potentially, depending on how much it costs to do that. This is an illustration of the JEDI mission, which is the densest sampling LiDAR there's been so far, as it goes across Milton Keynes in the UK. Every red dot is a measurement. Everything in between you have to infer via statistics. Leads to very large sampling areas, makes it very difficult to know the precise biomass and particularly the biomass change between two sites. So LiDAR data is really useful. It's the best way for doing biomass-bearer topography. It allows flood modeling, biomass mapping, biodiversity mapping. The problem is there is no globally continuous LiDAR data set. There's no long-term LiDAR data set yet either. And that's adding to uncertainty in this. So what we've been trying to do as part of GLAMS, working with Altair and others, is to go from what the current satellite LiDARs do, try and increase the coverage, to try and give us that, reduce the sampling area, give us the annual repeat measurements. And the way we try and do that is through photonics, trying to maximize the laser and detector efficiencies. You can increase the amount of ground you illuminate, the more efficient those two are. For the platforms, try and maximize the payload power and telescope area per unit cost. You can always launch lots of big satellites, but it's very expensive. So you want to maximize all this per unit cost. And then through signal processing, try and reduce the energy requirements to try and get the best measurement back with the lowest amount of laser energy. There's a paper here if anyone wants to read about that. Very simple equation. You just maximize all the maximize the top two, minimize the bottom one. So what we're trying to do as part of GLAMS, working with Fraunhofer Center for Applied Photonics, and I can see, I think, working with Coherent, I believe I saw a few people from there in the audience. We're trying to replace what the current satellite LiDARs use, which are these solid state lasers. This is the Homer laser from JEDI. It's about 30 centimeters long, about 5% efficient, very robust. Every satellite LiDAR so far has used a laser very similar to this. And we're trying to replace it with these small laser diodes. So there's one there, it's about 3 millimeters across in the red circle. The laser itself is 45% efficient. The driver is, we need to improve the efficiency of that a bit. The downside of those, they have much lower peak powers. So having to do lots of signal processing to try and get a decent measurement with this more efficient, smaller, lighter, cheaper laser. We were looking at using, on the left there is what the current LiDARs do, and they have tens of kilowatts of instantaneous power, something these laser diodes can never achieve. So we tried working at Ludwig Prada, came up with the idea of using pulse compressed LiDAR, very much like a radar. Unfortunately, it didn't quite work. You ended up with too many artifacts to try and see the ground under trees. But what we're trying to do now is a pulse train. So one of these on firing lots of little shots at the ground, keeping within the about 5 watt peak power requirement. That can build up over time a decent image of the ground, we think. Much more sensitive to background noise. This only works by night, but we think it will work from satellite. And there's a paper there by Hannes Hansen to explain that. We're also looking at trying to launch a constellation of these. Initially, we wanted to launch lots of small CubeSats. If you look at the numbers here, it shows how many satellites you need to cover the Earth once a year with a constellation of these. The satellites get bigger, you get more power, you get bigger telescopes, so you get more energy efficient, but the satellites get more expensive. And you can see here, you could do it with CubeSats, but you need tens of thousands, which would be prohibitively expensive. So it pushes towards a few larger satellites. We looked at using deployable optics as well, which would be brilliant. They would help us. However, the TRL is a little bit low, so we're sort of pausing that fight until later. And this is that paper there describing that by Chris Lowe, who was at Strathclyde. Now he works in the computer game industry, unfortunately. This here showing that as the satellites get even bigger, the power doesn't become the limit anymore. The instrument size and mass becomes the limitation. So we think we're settling on these 150 kilo class satellites, so medium-sized satellites. This is what we think a final GLAMS satellite will look like. 150 kilo class satellite with, we hope, a 10% efficient laser and driver, 58% efficient detector, operating in the infrared, building up an image of the world. And if we have one of these, we think we can build an image of the Earth every 5 years. And if we had 6, you can build the image of the Earth every single year. This is beating through clouds as well. So what's needed? So the things in green we have funded, working with Altair, working with Fraunhofer and other groups. The things in black, we do not have funded yet. So very interested to hear if anyone has any solutions for these. We're trying to increase the laser diode efficiency. We're aiming for 10% with a driver at the moment, using short 5 amp pulses on that. We hopefully get the instrument designed in the next year or so. What we don't have is more efficient detectors. We're using off-the-shelf 58% efficient single photon counting detectors. If anyone has more efficient detectors that work in the near infrared, about 850 nanometers, we're very, very interested to hear that. Deployable optics, very interested in that, if that can be done high TRL. We thought we'd reduce the number of fights we'd have to start with. We also need to maximize the payload power and telescope area for a given satellite size. We think 150 kiloclass satellite, and we want the maximum power for that. So really interested by the first talk, depending on how much that costs to subscribe to your beaming service. And we're trying to work up to launch, hopefully, via an ESA Scout in the next 3 years is what we're aiming for, but all dependent on funding. So thank you very much for inviting us.
Thank you very much, Stephen. Thanks a lot for your interesting presentation and interesting project. Any question for Stephen? Maybe I have one for you, Stephen, regarding your needs, and you mentioned instrument design. Can you tell us more about this? What kind of requirements do you have?
Well, so I'm an Earth observation scientist. We've done this very top down. We need a full thermal analysis quite soon is what we need to do, just because there's a lot of power going through this thing, and actually mechanically designing it, making sure we can focus the light on the ground, focus on the detectors. There'll be, we think, a bar of 30 of these laser diodes illuminating the ground, all held rigidly, and then aligned with 30 photon-counting detectors on the way back up. So that's working on now. Astronomy Technology Centre is hopefully going to do that over the next year. But there's a lot more thermal work to be done. If there's any clever thermal way of doing this efficiently, cost effectively, we're very interested to hear about that.
Okay, thanks, Stephen. Yeah, and Andres Fuentes from ASC has a question for you.
Yeah, thanks for that. Very, very interesting. Do you have any problems with the atmospheric turbulence? Do you have to use adaptive optics or anything like that?
Not really, no. It does attenuate our signal, but we illuminate a 30-meter footprint on the ground, and that's fairly stable. It will scintillate, I think, maybe 1 or 2 meters, but that's the least of our problems. So, I don't think we need adaptive optics. We would if we was trying to see, sub-meter resolution on the ground, but we're not trying to do that. Or sub-centimeter would be pretty small, wouldn't it?
Sub-centimeter on the ground? You're getting
we're going to have some 30-meter footprints on the ground. So as long as we can see that 30-meter footprint and know it came from there, we're happy with that. I think adaptive optics would be much finer than that, wouldn't they? I'm not sure what the sum would be as to when they would kick in, but we're not too worried about that.
And you're looking as a lighter, are you looking at like relative differences in height on the ground perspective?
Yes, sorry, I should have said that. I should have put more. So I normally give this remote sensing scientist. I'd gloss over some, but yeah, we fire the photons down and we measure the photon return as a function of range, photon return density. So we will see the full vertical profile of whatever's on the ground. So if there's a building, we'll see some off the roof, some off the ground. If there's a tree, we'll see some through the tree, some from the ground. We get the full profile back, and that's what we use to make our biodiversity biomass measurements.
Okay. Thank you.
Yeah, and as far as I'm aware, the atmosphere doesn't mess that up too much, as far as I'm aware, other than it attenuates the signal. If there's clouds, it's a different story, and we just don't see through clouds.
Yeah. Thank you.
Thank you, Andres, for the question. Any more questions for Stephen?
Right. Yeah. Thanks for the chat, Stephen. And it's good to see that that there are big. That there are requirements for kind of like pushing the power levels. I mean, how do you feel the power and your data, like the data rates kind of like compete, or what's like the biggest pull for for more power?
So at the moment, I said we started off with a fairly top-down approach, and the power limit is the current limitation on all the LiDAR satellites. We haven't yet addressed the data rate limit. You're absolutely right. The more beams you put out, the more data there is to transmit down to Earth. Now, we probably want to avoid onboard processing, because with a LiDAR, if you don't see the ground, that measurement's useless. So you probably want to repeat process the data and merge it with ancillary data to make sure you've really got that ground. So you probably want to beam all the raw data back to Earth. We haven't done that sum to work out at what point adding more lasers, we can't get the data back to Earth. One option we had, actually, these same laser units can be used for laser comms as well. So you can maybe occasionally point the whole thing off and fire one of the lasers to get it back to Earth faster, but that's off in the future. I'm afraid I don't know. That's the next phase we need to do, is the full constellation design. Chris Lowe did a little bit of work on that before he swapped industries. Oh,
fair enough. And Stephen, if you want to have a chat about satellites and different kind of constellation types, just drop me a line, and happy to have a chat.
Brilliant. Yeah, I'll look you up. Definitely drop an email.
Cheers.
Perfect. Thank you, Kevin. And regarding your needs, and you just show up, Stephen. I saw that you have some things about also lasers, diode, and I'm pretty sure that we could also introduce you to some interesting companies. So we stay in touch, and we'll see what we can do for you the next few days.
Yeah, always interested to hear about more efficient and more powerful lasers. Yeah.
Thank you. Thank you again, Stephen, for a nice presentation. Thanks a lot. And now welcome Jean-Luc Gache, founder and CSO of First Light Imaging. So Jean-Luc, you can start your presentation and share your screen.
Okay. You can see my screen?
Yes, not in presentation mode yet.
So, okay. Is it in presentation now?
Yes, thank you.
Okay, fine. So thank you, everybody. So I'm Jean-Luc Gache from First Light Imaging. We're a company based in France. We are a camera manufacturer. We are stemming from French public laboratories in astronomy. And we make cameras in the visible and in the infrared, mostly for adaptive optics in astronomy. We have recently been acquired by Andor and Oxford Instruments in Great Britain. And it turns out that a lot of people came to us and asked to turn our telescopes down and send them in space to observe the Earth and to detect greenhouse gas detection. Really, a lot of customers asked us, and we had to figure out what was the reason of that. So just at the beginning, what is the greenhouse gas detection principle? So you have the sunlight, it goes through the atmosphere, and crossing the gas, it gets absorbed by different species of gases and makes a spectral signature into the light you get. You have on the right the spectrum you get from various species, and the game here is to be able to detect and disentangle several species, and in particular the water vapor molecule, which has a high absorbance signature. It is the light blue curve, and in between those windows you are able to detect several gases. So historically the CO2 detection was in the 5 microns, so in the mid-wave infrared region. But we are not manufacturing cameras in that wavelength, and we search why people are now turning to the shortwave infrared, which is in principle less favorable, but there is a lot of advantages by switching to this window. So once you have this principle in mind, how do you detect greenhouse gases from space? Then you put a slit spectrograph in a satellite. The ground is lighted by the sun, go through the atmosphere, get the spectral signature, and your slit is moving on the ground. And for each image you take, you have a bidimensional image where one direction is the slit, which is moving on the ground, and the other direction is the wavelength. So you have a multispectral image or 1D. And by the displacement of the satellite on the ground, then you are able, by taking several images, to reconstruct a 3D image, X, Y, and wavelengths. And this has been demonstrated by the work of Al-Salam and published. Here you have the reference of the publication. It's more or less what we call a push broom imager. And instead of having a moving mirror to reconstruct the image, we simply use the satellite displacement. So what to do with this 3D image? Then you have for each pixel a spectrum. And in the spectrum, you are able to find the gas signatures. And it turns out that the SWIR region is very interesting to be able to disentangle several species. You have here an example of spectrum you get for several pixels. So on the left, you have with different curves, the different pixels across one line of the slit. And you see that the signature of the gases are increasing when you get to from the black line to the red line. And on the right, you have the details of one spectrum and the gas signatures. And Al-Salem showed that it was interesting also to have a high resolution spectrum of your observation to be able to disentangle the gas species and to be able to measure also the level of concentration. One point is why people are switching to shortwave infrared. That's because of the spatial resolution. So we have to come back to fundamental optics. So the angular resolution of an optical system is given by the diameter of the optics and the wavelengths. So it's proportional to the wavelengths and inversely proportional to the optics diameter. And if you observe at a very long distance, you see that you have to multiply by the distance, and you see that you need quite large optics if you want a high resolution from space. So this is what is stated in the graphs here. So I have plotted several cases of observation. And so on the right side, you have the resolution limit for a 25 centimeter optical system at low Earth orbit altitudes from 400 kilometers to 800 kilometers. And with respect to wavelengths, and as you are switching from short wave infrared, so around 1 microns, to long wave infrared, around 10 microns, you have a factor of 10, of course, in spatial resolution. So with 25 centimeter optics in shortwave infrared, you have a much more resolving capability than in mid-wave infrared or long-wave infrared. And on the right side, I've plotted the inverse problem. So given a resolution you want to obtain, so in this case 10 centimeter, what would be the telescope diameter with respect to the wavelength and the telescope altitude. And you see that if you are at a long wavelength, then to have a 10-meter resolution, which is the Copernicus resolution, so it is something that you should expect, then you need very, very large optics. Whereas in the SWIR domain, only small optics is sufficient. And this makes this compatible with CubeSats, whereas for longer wavelengths, you probably need a bigger satellite, which is more costly. And the advantage of CubeSats is that you can have plenty of them and have a revisit frequency, which is much higher than big satellites. Another point is the satellite speed. If you want to use a slit spectrograph, then the telescope is moving very fast when it is at low Earth orbit. And the resolution, the pixel resolution, is given by the speed, the apparent speed of the slit on the ground. And if you want to have also a spatial resolution, then you have to take the images very fast. And you have here the curve of the theoretical spatial resolution you get with respect to the frame rates of your telescope. So it's almost independent on the altitude from 400 kilometers to 800 kilometers. There's not so much difference. It's around 6 to 7 kilometers per second. And then if you want a 10-meter resolution, then you may compute that you need 700 frames per second to be able to have this spatial resolution on ground. You have here the curve of the spatial resolution with respect to the frame rate of the detector. So all those conclusions are that hyperspectral imaging is more favorable in the SWIR band for high spatial resolution. There is also some other advantages, like be able to disentangle more the gas spaces, but I'm not a specialist of that. The problem is that at long wavelengths, you need very large optics and costly that are not compatible with CubeSat and low-cost missions. And also, you need a high acquisition speed to get high spatial resolution that you may need for your detection. So if you come all those parameters together, we are the people that are able to produce such cameras, because it is the kind of technology we've developed for astronomy and for adaptive optics. And it turns out that we had to develop one of our camera for those space missions to adapt it for space use. This is what we call the C-RAD new space. So it's a short-range infrared camera that has sensitivity from 1 to 1.7 microns. And because it was designed for adaptive optics, it has also a very high acquisition frame rate, up to 600 frames per second. And this last point is decisive for people that want to integrate this kind of technology in CubeSat for LEO orbit observations. And this is what we can bring among several other advantages, like low noise, low cost, and customization for a space mission. And well, that's it. And thank you for your attention.
Thank you very much, Jean-Luc. Thank you very much for introducing us this nice technology. Any question for close light imaging for Jean-Luc? Maybe one from my side, Jean-Luc, more general, more global, but can you tell us more about how many projects do you run in space? Is your technology already involved in space industry, and how many projects do you have?
Yes. So the first project we worked for in space was for optical free space optical communications. Because there is a need of adaptive optics in this for this topic. So we were with our products which were developed for adaptive optics. It was ideal. So we developed, we adapted one of our cameras for a space mission. I'm not allowed to tell who and the mission name, but we know that we will fly next year. And then we had a lot of contacts, I would say 5 to 6 different companies that are working with us on this greenhouse gas problematic, because you know that the regulations will come in the very near future, and it's a major concern of authorities, and being able to locate the greenhouse gas sources and to fix them is one of the main topic for the authorities in the coming years. So a lot of companies are willing to send constellations of satellites, and then they need this kind of technology.
Thank you, Jean-Luc. We have a question from Yves Pommier, institutional. If you like, would you like to ask your question by yourself? Can you unmute yourself and ask it? No. Okay, so I will ask it for him. So would you be able to observe the destruction of OH by H2 in the upper atmosphere?
Sorry?
Would you be able to observe the destruction of OH by H2 in the upper atmosphere? You can see the question in the chat.
Okay, so I'm not a specialist of that. So if there is a signature into the shortwave infrared of that chemical reaction, then probably we will be able to detect it. But I am not, unfortunately, not the answer now.
Mm-hmm. Another question from Yoshiaki Shikata from Sumitomo Electric. How many pixels numbers do you need for this application?
So we have a 640 by 512 sensor pixels. We know that it's a bit tiny for the application, and people would like larger sensors, but unfortunately there are not so much sensor available on the market. So one of the solutions is to use several sensors all together, and as it is very cost effective, it's quite interesting solution compared to a larger device.
Thank you, Jean-Luc. Yes, Andres from AEC.
Yeah, thanks, Jean-Luc. Just since I brought up the pixel numbers, what's the pixel pitch of your sensors?
15 microns.
15 microns. Okay, thank you.
Thank you, Andres. Any other question? Okay, so thank you again, Jean-Luc. Thank you very much for your last presentation. Thanks, and now welcome Matthias Beer, CEO and co-founder of Space Optics. So Matthias, you can share your screen and start your presentation.
Yeah, thanks, Jeremy, and good afternoon, everyone. I'm trying to share my presentation. So hope you can see that in full screen mode.
Yes, can start.
Okay, perfect. So yeah, nice to virtually meet you all, and good afternoon. And thanks for the opportunity to present a little bit here our company Space Optics and our technology on the engineering and fabrication of metallic mirrors and telescopes for Earth observation from ultraviolet to infrared. So starting maybe with a background on the company, because we are not that old and probably not all of you have heard about us. So we are a spin-off from the Fraunhofer Society, more precisely from the Fraunhofer Institute of Applied Optics Precision Engineering in Jena, Germany. And we've been founded roughly 4 years ago with the goal to transfer the technology on engineering and machining of very high quality metallic optics, so components and systems from applied research to industrial production. So the push for that was clearly at this time the whole new space rush. So customers were asking for a serial production of optical mirrors, space-grade mirrors, and also optical systems, so telescopes, camera optics for Earth observation, optical communication. And we were 4 founders working for more than summarized 50 years on making metallic optics for space. So the idea was, okay, let's do that on a commercial way, spin off the company, go out from the Fraunhofer Institute. We started that business in an own fabrication site, so which is close to Jena. So every one of you who has been in Jena, Thuringia, right in the center of Germany. So we were 20 minutes west from that. We have a large fabrication site, roughly 3,000 square meters, and started 4 years ago to build up our own optomechanical workshop. So we installed a lot of equipment here, being able to produce this kind of metallic optics with CNC machining technology, diamond turning, diamond milling capabilities, polishing equipment, clean room, and a lot of metrology to measure these mirrors and to measure the optical systems that we do. We're coming from a scientific background. So before we founded the company, we were always working on metallic optics, mainly on scientific projects, on scientific missions, mostly one-off systems, very effortful, long-year projects, and we've been involved in several remote sensing projects, but also hyperspectral imaging, optical communication, interplanetary missions. A couple of them are listed here. So we've been involved, for example, in different Sentinel missions for ESA, and also on an altimeter for JUICE, so going to Jupiter. And it took us roughly 2 years to start a business, to get the equipment running, to have the floor ready, and then from 2022 roughly, we're really able to now offer series production of metallic optics, so high-grade mirrors, mirror systems. We have nowadays produced roughly 3,000 mirrors, and we know that about 350 of them are in orbit. We don't know about all of them, but it's quite a cool number for this short time, and we're also introducing our own products since last year. So taking maybe the EPIC slides, the EPIC question already at this point, what can we offer to you? So what are our products and capabilities that we do? So we roughly have 3 lines. The one is that we just sell optics from stock. We call it stock optics. So that means standard mirrors, standard telescopes, but high quality. So like, for example, these off-axis parabolic mirrors that you see over here, we have a bunch of those optics available also on online platforms like Meet Optics. So it's roughly what you also get in the Thor Labs catalog, but on a higher quality in terms of surface form and surface roughness. So these are mainly nickel-coated mirrors, polished and figure corrected. So if you need such a mirror for a high-quality application. Second line is build-to-print manufacturing. So we do that a lot. If the customer comes and just has a finished product, a finished mirror, optical system, then we just build that from the technical data that we receive. This is an example of 550 millimeter freeform optics that we did on one of our diamond turning machines. It's not for space, it's way too heavy, but it's for lab application. But it shows roughly the largest size that we can do. So we are limited to this 550 millimeters. So nice freeform optics manufactured here. And the third line is more regarding core engineering cooperation projects. So as we are coming from Fraunhofer, we're used to work in research projects and also in joint industrial consortia. So bringing our expertise from manufacturing into, for example, a system development. And this is an example here of a small sat payload that we develop in a consortium together with another company from Jena, Quantum Optics, and also the Fraunhofer Institute, 2 other companies, and under a DLR funding. And this is a small payload that should do entangled QKD from a CubeSat at one day. So I took 2 examples. I just have 2 more slides showing a little bit the capabilities where we could probably help the community with our technology. I divided that by wavelengths. So I took here a system that is more targeting the long wave infrared for another Fraunhofer spin-off, Constellar. They're located in Freiburg, Germany. They also founded roughly at our time 4 years ago, and they want to monitor the land surface temperature. So for agriculture from space in the long wave infrared. And in a joint project together with 2 Fraunhofer institutes and Constellar, we developed a small imaging payload, so small TMA telescope that you can see over there, that was designed by the Fraunhofer Institute in Jena, and we took over the manufacturing of those of this instrument. And I hope you can see my mouse, and here it's integrated in a 3U platform, so roughly shoebox size, together with the detector and also the electronics here in the back. And the beauty of that is that it basically consists just out of 4 components. So we have 4 mirrors, two freeform mirrors, another aspheric mirror and plano mirror, and very precisely machined housing that you can see here in black. And the whole integration is actually done by the precision of the interfaces and the relative position of the optics to that interfaces. So actually everything is fixed by ultra precisely machined optics and interfaces. The integration of that telescope could be done within a couple of hours. So using this technology, you can simplify a lot of your system assembly tasks dramatically. And what we do offer here in terms of that infrared optics, actually we also co-engineer, so we take over a little bit of the system engineering, and then we offer the complete optics manufacturing, which is mainly CNC machining, thermal treatments of this special aluminum alloys, diamond turning, diamond machining, qualified cleaning, coating, and also system assembly. So we also measure the system performance, MTF, wavefront, and deliver to the customers the finally integrated telescope. Second example that I brought with me is a bit more effortful. So if we go to shorter wavelength applications like ultraviolet visible range, then usually the quality that we can achieve with diamond machining technologies is not good enough. So we need better surface form, better surface roughness results. And the standard way to achieve that is that you plate your optics in the most cases with a layer of electrous nickel. And this layer acts as an amorphous intermediate layer that can be diamond machined and polished and also figure corrected to very high qualities. And this is one of our standard technologies, also fully space qualified. I have a nice picture of a larger mirror over here. So this is also part of a hyperspectral imaging telescope. So it's the primary and the tertiary mirror of that telescope. You can see it's again machined on a common mechanical platform. So this is a special technology that we do so that we can already fix the relative position between those mirrors with the precision of the machine that we use actually. So you don't have to align them at the end. You see it's nickel plated, diamond turned and polished. And actually using that technology, we can achieve very similar results that we also could do on glassy optics or ceramic optics with the advantage that at the end, this is more tailored to mass production and to strongly freeform aspheric optics, also to cost-effective optics at the end. That's why this technology is so interesting for constellations nowadays. Maybe a word on the quality that is achievable. If we go with this functional layer and then adding polishing and figure correction technologies, then at the end, the surface form that we can achieve is more or less limited by the metrology that we have available for measuring the surface form. This is an example here down right, not of that mirror, but of a very extremely plano mirror that we did. So this is 85 millimeter aperture. And this was measured and figure corrected to surface form of about 1.5 nanometers RMS. So this is then more or less limited by the interferometer to measure the surface form. And with our polishing technology, also on the roughness side, on the small scales, we're working down to better than 0.2 nanometers RMS if needed. So this is roughness on a range of 170 by 170 microns. So what could we do for you here at this point? Again, system engineering, also complete optics manufacturing for short wavelengths operations. So CNC machining, diamond turning, plating of the optics, polishing, figure correction, and at the end also we integrate their telescopes and those systems delivered to the customer. We're only working on the passive part, so we're not dealing with detectors and not dealing with electronics. This is something that we would like to cooperate. This is then what do we need from the EPIC members. And with that, I would like to thank you for your interest, and I'm happy to take questions.
Thank you very much, Matthias. Thank you for your presentation. Any question for space optics for Matthias? Matthias, one from my side. You mentioned the biggest size of mirror you are able to provide. What is the minimum size you are able to produce?
Yeah, that's a tricky question oftentimes, because oftentimes the smaller ones are more complicated than the large ones. I would say that depends on everything that we can still clamp on the machine. It's more the clamping technology at the end. In terms of structure size, we also worked on directly diamond machine gratings, so microstructured optics in electrous nickel plating. That works quite well. In terms of aperture size, millimeter, even smaller. Okay. So we're also making molds, for example, for polymer optics, and these are oftentimes even smaller than a millimeter.
Okay, thank you. Any question? Okay, so thank you again,
yep.
Matthias.
Thank you so much.
Thanks a lot for your participation and presentation. Thank you very much. And now let's move where last but not least speaker of the day, Trond Loki, CEO of NEO, North Electro Optic. So Trond, are you here? And if you're here, you can start your presentation and share your screen.
Yeah, I'm here.
Hello.
Can you see my screen?
Yes, can start.
Great, thanks. Yeah, so I'm Trond Løke. I'm the CEO of NEO. That's short for Norwegian Electro Optics. So we are, amongst other things, designing and producing the hyperspectral imaging systems called HySpecs. Just start with a quick intro of NEO and HySpecs before I will talk about our stratospheric and space activities. And in the end, just a short reminder about data quality. We are almost 40 years old now, spin-off from the Norwegian Defense Research Establishment. We are doing everything in the world of photonics, I would say. We are a research-heavy company, but we always do our research with a goal to develop kind of commercial products. One of those commercial products are HySpecs in the hyperspectral imaging market. We have headquarters in Oslo, a sales office in the US, and a subsidiary software company in Sweden. In Oslo, we have 60 employees, half in R&D, and we are growing fast, as I said, and our owner is a non-profit foundation with a vision of supporting both art and physics. So it's a nice owner to have. We are doing, as I said, we are research heavy, and we are doing a lot of projects, EU and international R&D projects. We have done that since 39 years ago now. One good positive thing about, I would say, collaborating with us is that we have all the resources internally to design, develop, and produce all our electro-optical products. Also sell them. All systems that we make today, hyperspectral solutions, are push broom systems, except one actually that we are starting very soon with somebody here also, or some other participants here. But we have focused on the push broom because at that architecture you are capturing a narrow line on the scene and all the spectral information at the same time, meaning that, that has the kind of the architecture with the highest spectral fidelity per pixel. We are offering kind of multi-scale offerings all the way from laboratory, field to drone, airborne, stratospheric, and satellite. We flew our first system 21 years ago. We flew our first UAV system in 2012. We flew our first stratospheric system in 2022, and we will fly our first satellite mission next year. So now I will focus on what we do in the stratosphere and on satellite activities. We delivered our first stratospheric solution to USGS in 2022. It was a customized version of a Mjolnir V1240, a visible near-infrared solution from 400 to 1000 nanometer. It was especially made for this Swift hail drone with a 3.5 kilo solution adapted for the nose here. But we flew it in 2022 on the NASA ER2 platform. Of course, it's a huge one relative to this one, so we had a lot of space. And today you can get all our drone and classical system as a kind of stratospheric solutions. There is some adaptation to focus where you focus the system, and some adaptation to cooling and heat dissipation when you go to stratosphere, as you all know. This was a big deal for us in 2022. Our first images from stratosphere. Yeah, it was no adaptation on the field of view, so it was quite coarse resolution. It was 5 meter, and it was in the visible range, as I said. But nice and crisp images. We showed that we could give very sharp PSF at this altitude. Last year we flew again in the stratosphere on the Sky high altitude stratospheric platform. It's a cool platform where you can fly very slow, and meaning you can get very nice SNR levels for a decent pixel size. And we're flying again with Sky in June for methane emission, special custom designs of our shortwave infrared cameras. And when I say shortwave infrared cameras, I mean up to 2.5, so extended sphere, which is called these days. Then I will say a little bit about what we do in space. Our biggest activity is a project called HyperNor. It's a ESA in-orbit demonstrator project where we are designing a shortwave infrared camera with good GSD for this size. You can see a CAD model on the right side here. I'll come back to this project. For the last 5 years, we had support funding from the Norwegian Space Agency, and this year is no different. We have 2 projects today, or this year on this. It's methane detection and high specs on the moon. We are also starting a new activity very soon with some of the participants here in this meeting as well. It's a EDA-funded project called HyperIP, where it's kind of a hyperspectral camera for space for defense applications. And last year we signed our first commercial space contract with launch already next year. So we're delivering an engineering model in 10 months and a flight model in 14 months for that project. We also have other commercial activities that I cannot say now. Yeah, HyperNor, the main kind of what's called goals there is to develop a low cost, low weight, low volume hyperspectral imaging system with a competitive performance. So of course not easy, but we believe that we have some specs that is fitting those criteria. Our goal was to produce something that is less than 20 kilos. We are ending up with something around 6 to 7 kilos, which we are happy with. And also our goal here is to have a low risk solution, meaning that there's a lot of new optical components that haven't been tried before. This is just a 3D printed version of HyperNor on the right side, but yeah, we are currently in the phase where we are getting offers from optical suppliers on the optics here. Yeah, it's a novel design with a dual slit solution. 9 meter GSD from 500K orbit. With a dual slit, we can use super resolution to get 4.5 meter, so 1280 pixels. Only 36 spectral channels. I would like that to be more, but this is the compromises you do, right? It's from 950 to 2500, and I think with a very impressive spatial and spectral misregistration, only 1% of a pixel and 1% of a band. MTF as Nyquist is larger than 0.21, and here you can see the SNR values for 100% and 20% target. The size is here, the weight is here. We hope to launch this in 2027. That's pending from ESA activities. We also have some customized off-the-shelf components that we are launching in shorter time frame than 2027. Yeah, we have are customizing a 3640 with a field of view reducer and a kind of telescope for methane detection, and we are also doing some other adaptation to that systems. We have a customized 3640 with a space grade detector. There we are on InGas, only up to 1.7 with launch next year. And we have a customized veneer solution, 400 to 1000 nanometer. And we I'll do some customization also to put HySpace on the moon. Yeah, and just in the end, I like this slide a lot from kind of a quote from Joseph Boardman, which I guess many of you have heard of, the four hurdles of imaging spectroscopy. So that when you're making a hyperspectral solution, you need all your pixel to be uniform out of the box, or after the processing steps. You need it to be stable with pressure and temperature. Of course, the temperature is most important here. And of course, you need a traceable calibration so they can use the data for some scientific usage. And in the end, you are dependent on having, of course, a decent signal-to-noise ratio in each band. If you can't do this, there's no point, I think, in launching something to space. Thank you. Any questions?
Thank you, Tron. Thank you very much. Really nice to see that you have some project on space. Any question for Tron? So I understood that it's a new activity now for you, space, or at least a recent activity. How did you face all the challenges? Because we all know that it's a difficult field of activity and with a lot of requirements. So how did you manage?
Actually, the activity we started with in 1995, actually, with just some theoretical studies for ESA. That was how HySpace came about. But then at that point, we were so small, we said, like, we don't have resources to go to space. And it was all space, right? So let's do airborne and go down from there. And now that we have grown quite a lot, and yeah, you have not only old space, you have the new space thing as well. It's easier to put things in space, right? And we always had that in mind with the robustness and reliability of our cameras. So yeah, there is, of course, some additional problems with heat dissipation and stuff like that, putting Stirling colors and whatever in space, which yeah, it's yeah, we are solving at the moment.
And how the photonics community or the EPIC community could support you in facing all these huge challenges you have?
No, I think yeah, we are, as I said, we are looking for optical suppliers in space. We have, I think we have gotten some offers already, but for the engineering model. But yeah, that is of course something I hope people can help with. I see also on the participant list there's a lot of detector and sensor suppliers, which I try to keep in contact with regularly. So I think there's a lot of synergies here between participants and us in NEO for sure.
Of course. And yeah, we have a question from Yoshiaki Shikata, Sumitomo Electric. Do you employ MCT detector for the space grade?
Yeah, so all these projects that I talked about, the SWIR project here are MCT detectors. They are 640 or VGA resolution, 10 micron pixel pitch for all of them.
Good. Okay, any other question for Tron? Yeah, I have one more because I'm still wondering how all the data are managing, because you produce a large amount of data using space spectral imaging. So how it is done now? How do you manage to process with all these data?
Yeah, that's the big question, right? We are in Hypernor, for example, we have the Norwegian company, a part of the project for the onboard processing and also dimension reduction and the data downlink, right? So, but yeah, for sure, it's a huge amount of data, right? We are capturing at 700 FPS, 640 times. It's only, I think it's 76 bands or something because we're covering 2 slits. So yeah, but it's still a lot of data. So you cannot acquire like the full orbit 100% of the time. You don't have capacity to downlink everything, basically, the way it is today. Yeah. But hopefully that there's a lot happening there as well. And yeah, and on the compression side, at least previously, compression was seen as yeah, you are not allowed to mention compression in the hyperspectral community, at least not from airborne and down. But I think it's more common in the space business to do some compression as well.
Thank you, Tron. Thank you again for your nice presentation. Thanks a lot for your participation. And now we are arriving at the end of this meeting. So I would like to thank all the speakers for this today's event. Thank you very much for your participation. Thank you also to all the attendees and for your question and interaction. I would like also to mention that we will organize, and it's now official, we organize a space day, a space meeting in September at the European Space Agency on one day. And we'll start to work on it the next few weeks. So yeah, I invite you to check our website and the event we will have. So it will be on one day, and I think it's on the 17th of September. But we'll hear about it in the next few weeks. So we'll keep you posted. Okay. So thank you very much to all of you again, and see you next time for an interesting event on space and new space. Thanks a lot.